Hi everyone, my name is Xavier Williams and I'm a graduate student at Michigan State University in East Lansing, Michigan, United States. And today I'm going to be talking to you about analysis of affordance detection methods for real-world robotic manipulation. So as just a general motivation, today I'm going to be talking to you about smart object manipulation, which is the process of endowing robots with human intelligence. So humans have the innate ability of, whenever they see an object, whether they have previously seen it or not, they know how to interact with an object based on past experiences. And we want to give robots that ability as well. And this whole process is an increasing trend in the robotics field today. We give a special attention to object manipulation because it's relevant in a variety of different domains, from everyday tasks such as preparing food to the dangerous and otherwise non-human friendly, like handling nuclear wastes. So also the point of this talk is to organize affordance detection methods because no such collection currently exists. So we also want to provide a clarification of terms and just like a general framework by which these manipulation schemes work. So through all this, hopefully we can aid robotics researchers by providing an analysis of trends and then identifying areas that are in need of further research. So now that we've gotten the motivation out of the way, we can now talk about affordances and then the rest of the talk as well. So what are affordances? Affordances are the set of actions that are allowed by an object. As you can see by this hammer right here, it has a variety of affordances from striking to wedging to grasping. And so the affordances are also a function of an object's geometry. So based on the way that it's shaped, it affords different things. So as you can see, striking is afforded based on its flat shape versus wedging through its wedge shape and grasping through its handle-like shape. So through this, you can see that a object affordances are a function of the object's parts as well. So when you think about affordances and grasping, there are two main schools of thought. That grasping is in and of itself an affordance, which is the idea that every object can be grasped, which is true. But we like to think of it as in like grasping is related to all other affordances, which is the idea that every affordance, in order to execute it, needs a grasp to back that up. So starting from this framework down here on the slide, starting from the object and the object's parts, you extract the affordances, and then those affordances are what are used to inform the grasp synthesis. So when you talk about handwriting versus swinging a hammer, those require different grasps, and so you want to use those affordances in order to inform those grasps. So then you can execute the affordances at the end of this framework and execute the tasks that you're trying to accomplish. So now let's get into how you actually detect those affordances. So here's a general framework of how the detection process works. So you start from the image database. It goes through pre-processing steps, and then from the training images, you propose what objects are in the image. You extract the features by using neural networks or geometric methods, and then you actually use those features to train the affordance detection models. And then once all that is done, you use classification methods to rank the affordances that are in the object image to result in the final affordances that can be used later down the pipeline for grasp synthesis and then affordance execution. So there are different ways that you can input data into these models. There's a variety ranging from 2D all the way up to video. So for 2D inputs, you can use RGB or YUV values based on your motivation. RGB is by far the most popular, but some methods use YUV representation because it separates color from intensity. One of the problems though with RGB values is that it is not tolerant to self-occlusion. So when you have objects based on a 2D image, you can't see what's on the other side of the object because it itself is occluding what's on the other side. But this is solved by using 3D inputs like RGB-D information or point clouds, where you have like an actual 3D model of the object or just depth information in general, where you can then have a 360-degree view of the object. This self-occlusion problem is also solved by video methods that use multiple viewpoints to show what the affordances are. So They also have a demonstration of the affordance being executed so that you know what grasp it is and also the entire scope of the object so that you can have more information to feed into the feature extractors later down the pipeline. So as far as preprocessing goes, these steps are with the intent of making the objects more applicable to the real world, because in the real world, you have a variety of brightnesses, rotations, translations with respect to the camera frame. So all these different ways that you pre-process the image try to get at that, whether it be changing the contrast of the image, the saturation, or adding just noise into the image in general. So all these different things try to make the image more like what you would find in the real world. So when you think about affordances in general, there's a couple ways to think about it. You can either represent the object by its parts, which is the most popular way, and then assigning affordances to those parts. Or you can think about the object as an object as a whole. So thinking about the fact that like this object is in and of itself a tool by which you can execute a task, not considering these subparts. This is relevant like when you have a soccer ball, for example, when it doesn't really have any parts. But typically, when an object can be decomposed into its parts, that is what is used to find affordances. Because that's a more interesting problem in general anyway. So the way that they actually extract the features in the affordances is they use either computer vision or geometry ways. So they use neural networks or popular feature extractors like SIFT and HOG that can detect different surfaces on the object and rank them based on what is actually present. Or you can use geometry methods that are ways of representing the object by the combination of shape primitives, for example. So you can use spheres or cylinders to reconstruct the object where you have certain affordances based on those specific geometries. You can also use surface normals or the curvature of an object, but these incur higher overheads because they often use machine learning if you don't have that 3D information going into it. However, using surface normals are helpful because it gives you information about where the object is in relation to your end effectors. So it can inform the graph's direction, for example, which is helpful when you evaluate these affordances in real life. So now let's get into the training of how you actually train these models. So there are two main ways by which training methods vary. There's the affordance learning, which is using annotated images versus affordance demonstrations, or you can use architectural complexities variations, so whether it be sequential or end-to-end architectures. So as far as affordance learning, you have pixel labeling, where each pixel in the image, is labeled with an affordance. So as you can see in this example here that's pulled from the UMD dataset, which I'll get into later, each pixel is labeled with an affordance, which is then fed into the feature extractors. On the other hand, you can also use interaction-based methods where you start from an interaction image and then you exploit the geometric information from that by using shape primitives or surface normals. Use those informations to predict the affordance candidates and then rank the highest affordance based on what is most likely to be moving forward. And then you have the architectural complexity of the training method. So you can have sequential methods which do use the object detection and the feature extraction methods that I talked about previously, which are intermediate steps from the beginning to end. Or you can use an end-to-end method that goes directly from the pixelized affordance labels directly to the affordance predictions at the very end. This is more applicable to real-time applications because it's all in one step. So when you're talking about data sets, here's on this slide has a general list of the most popular ones. The two most popular being the UMD and the IAF data sets. As you can see, there's a wide variety in the number of images that they have. And something unique about the UMD dataset specifically is that it uses a Connect sensor made by Microsoft to create the RGBD values that are featured in the dataset. They do this by mounting the Connect sensor and then having the object that is in the image on a rotating surface and then rotating it a full 360 degrees so that you have the entire point cloud representation of the object. The IAT-AAF dataset is popular because it contains cluttered scenes, which is very important because it mirrors the real world as well. So now let's get into the kinds of classifiers that are used for this. So there are just a limited number of classifiers that are used. Random forest between structured and conditional, convolutional neural networks, deep neural networks, or a combination of the above. It should be noted that random forests generally have weaker performances because they heavily rely on hand-coded features, so they're not really robust to objects they haven't seen before. But the convolutional neural networks and the deep neural networks learn to understand those features, so they are more robust in this way. So now let's get into the evaluation of these detection methods. So some general statistics that most of these approaches use, they use precision, recall, and F1 score. Precision being the percentage of true positives of all positives, recall being the percentage of correct predictions from all predictions, and then the F1 score being a consolidation of those two previous methods to output a accuracy measure. F1 scales from 0 to 1, with 0 being a completely inaccurate model to 1 being a very perfect model. And then this slide contains a comparison of operation on the UMD dataset that I described before, where you have the UMD dataset that contains 5 main affordances: cut, scoop, contain, pound, and support, over 28,000 RGB-D images featuring 105 objects with each labeled affordance at the pixel level. So as I said before, the structured random forest, which is in the leftmost column, has the worst performance because it's not robust to new objects. However, the combination methods like the CNN plus the conditional random forest has the highest performance because it has a special architecture that that exploits these new object features that the method hasn't seen before previously. So now for the conclusion. So as we have seen previously, it's now possible to endow robots with human intelligence, which happens at the pixel level. So you give robots the ability to understand objects as humans do by labeling the affordances at the pixel level. This is done either by hand or through neural network artificial intelligence. Neural networks, though, are the best tools for affordance detection because they are the most robust to new objects. They have the most variability when it comes to new features or adding in different new things, as opposed to random forest implementations. The key challenges for detection methods, though, are as follows. So only really the IAT-AAF dataset contains cluttered scenes, and these, like I said previously, mirror the real world, because the real world doesn't always have very structured, very clean scenes. So you need to be able to understand what affordances are, even if the object might be cluttered or have occlusions in front of it. Also, there can be more complex affordances be detected from images. So far, it's really just cut, grass, contain, but what about if the object can be foldable, or if it can expand, or if it's breakable, for example? These things aren't really explored, but they could be explored more. So as far as future directions, you can use the affordances to form grass synthesis. So once you have the affordances, then determining how you can grasp the object in order to execute that affordance in the best way. Also, since each robot manipulator is different and unique, you can tailor the affordances for each of those unique manipulators, whether it be an end effector with 2 or 3 grasping points. Also, there can be more validation on physical robots. So it's one thing to detect the affordance of the object, but it's another thing to actually carry that out in the real world, where you have that domain shift between simulation to the real world and understanding how you actually can grasp the object in real life. So hopefully from this talk you've gained an understanding of how you can how robots can understand affordances. Thank you for listening, and are there any questions? Thank you.